In this video, I would like to show how to compute critical objects in RayJack ONE and how to display them graphically. As an example, I use this very simple double Gauss system, which you can also find in your example database. Critical objects are objects that can be seen from the detector, the image plane. When you look into the system from there, they are important because when they are also illuminated, they may scatter light directly to the detector. Now, as a basis, I used this simple script to set up the geometry. And now the trick with critical objects is that you make the detector, the image plane, a light source. In RayJack ONE, that's very easy. You create a source object and give it a name. Let's call it image plane. And assign it to the image plane. Now I know from having had a look at the geometry that it is already associated with a very variable named image plane. Then I have to specify the location. That means the direction in which the rays will go. And we would like to send them to the negative hemisphere. The number, then the number of rays. Let's use 2000 to get started. The wavelength, for which I will simply use 550 nanometers. That's it. Now let's see the effect. In order to do that, I could now view the system again, but it's advantageous to make the system view directly in the script. So this creates the system view, and now I add the light source, viewer add, rays, source rays, and you will immediately see when I run this script that this is not an optimum choice. So here you have the system and the rays go in all directions. But of course, it only is interesting if we have the rays going into the lens. Now, let me have a look at the system in a profile view. It takes a little bit. And then you see that we only need rays that are directed towards this entrance, and here you see the coordinates. When I look here, the exit part aperture of that system is 75 in in horizontal direction and 23.5, say, in vertical direction. So what I will do is I add a curve, which I will use for importance sampling. It's a curve, a three-dimensional curve, and it's circular. And the radius was 23.5 millimeters, and the axis is the z-axis. And with the position, I think it was 75 millimeters, but we'll see in a few seconds. So when I have defined that curve, I can now set it as a target for the source. And this is done with this command. It's a target curve. And I enter the curve as the argument. Now, I would like to show you not only the rays, but also the curves, the curve which I add to the viewer. Otherwise, the viewer only shows the physical objects and the sources. Let me save that and run it. And then you see that we are already in a good position. Now you see that the rays are all directed towards this red curve. And in principle, we could already do a ray trace by clicking here just to see what happens. This takes a little bit, and you see it's exactly what we wanted to have. So let's go on. By the way, here you have a list of all objects that have been hit by rays, or where rays have stopped. And you see, these are exactly the critical objects. So in reality, you would use many, many more rays and possibly use no graphics. But yeah, it's already in some sense the solution. Now the lens one front, that's the front surface here, that's not really interesting here. So we will now leave it out when we are working on the graphical representation. Let me close a few windows here, go back to the script, and instead of using the graphic user interface, I make here the ray tracer as a ray tracer non-sequential, give it a name, tracer, and now I assign the viewer so that we have everything together. Viewer, and yeah, that's it. And trace. So then we just have to click on run to make everything work. Now I would like to display the spots that these rays have caused on the objects graphically. In RayJack ONE, we have many types of detectors, and the detector I will use here is one which simply collects the rays on the objects. Let me call it RC. It's a detector ray collector. And normally we assign such ray collectors to specific surfaces like the image plane or whatever. But here we do not assign it to a specific surface. And then it is use global. Now we have seen that the lens front is not really of interest. Therefore, we exclude it actually from this detector by setting a ray filter. And in this case, we use the current object filter. So we would like to have all rays with current object. And here we have a comparison, as you can read off here, comparison. And I do not want to have not equal the lens front, which I simply copy here. And so now, once again, we collect all the rays in ray tracing, except those that have hit the lens front, because we are not interested. Now, I would like to make the ray tracer a trace and afterwards show you immediately the result. So here, once again, we simply redo the ray tracing. I made a typo. I called it here tracer, trace, but it should be tracer trace. Let me simply run from here. Which takes a short while. Then we have our system view again as before. Now, in order to see the rays, let me simply add something here, make it second viewer, or let's call it critical, is system view. System view. So this will just show the geometry as before, but now we add the rays that we have collected. Ray collector, that's the object, the rays, and we do not want to show the rays, actually, we want to show only their positions. So when I enter P, I finally end up with positions. So no need to run the full simulation. I just want to see the result of that. Let me do it by run selection. Okay, now let me open the system and you see where the spots are. In one of the next videos, I will then show you how to compute the illuminated objects, but it's more or less trivial. You have to place the light source here. And the interesting thing is then to find out which objects are critical and illuminated because they are dangerous for stray light. So thank you for your interest in this.